Thank you, Marco, for your kind introduction, and good afternoon to everybody. So today I'm going to describe our techniques for natural language processing for the analysis of policy text. And in particular, it's a quite different perspective with respect to the previous presentation. We are not using deep learning techniques, but it's another bunch of techniques taken by natural language processing, and I will present the semantic framework tool. The semantic framework is the main backend of the platforms developed in the context of the two horizontal projects in the InterRegMed program. The two projects are Thalia and Social&Creative. The main goal was to provide some pilot services for different kind of stakeholders, such as the project partners, the policymakers, for supporting different activities, such as the community building or the thematic engagement and the facilitation of interaction. In order to achieve those goals, we have analyzed all the results which have been produced by all the projects in the context of the Interreg Mediterranean program to define what we call the semantic model. That is a structured representation of concepts along with their relation. In this picture, I will show you the main pipeline implemented by the semantic framework. First of all, we gather a collection of documents. So we gather all the reports and the deliverables which have been produced during projects belonging to the different communities of the InterRegMed program. We also gather some policy or scientific manuscript and articles, and we group all this document in a collection of documents. After that, we performed a quite complex natural language processing pipeline in order to identify and extract the most important concepts from the textual content of documents. For us, a concept is an atomic textual unit occurring in documents, which could be composed by a single word, but also by a sequences of words. And then starting from this list of concepts, we generate a semantic model, which tries to arrange all the words, sequences of words, but also text fragments and word documents in a kind of geometrical space. In order to build this geometric space, we rely on the so-called distributional hypotheses, which claims that the meaning of words is given by their use. So terms which are used in similar context share a similar meaning, and they will be arranged very close in that geometric space. So by analyzing, for example, a huge collection of documents, we could say that, understand that, for example, beer and wine are different words, but they have a very similar meaning, since they usually co-occur and are used with quite more or less the same words. For example, drink, glass, party, pizza, alcohol, and so on. This is the main intuition behind the distributional hypothesis. There is a lot of math behind these techniques, but of course I will not provide you with all these details, but I will show you concrete examples of services which were built by leveraging the semantic framework and the geometric space I told you before. So this is a set of, these are the services which were built for the Thalia and the Social&Creative projects. I will start with the demo of smart search and then the policy design variable. I hope everything will work properly. I start with the smart search. The smart search service provides two main services. The first service is a semantic search engine As the previous speaker told you, the semantic search is able to return documents according to their semantic relatedness and not the exact matching with the query terms. So differently from a classical search engine, which returns documents if and only if query terms occur in the documents, a semantic search is able to return documents which are somehow correlated to the query terms. And the second service, built, of course, on the ground of the services provided by Semantic Framework, is an automatic summarizer of documents. Each document can be automatically summarized to produce a shorter version of the document itself, of course, by preserving its meaning and the key contents of the original text. We can summarize on the fly documents which are tens or even hundreds of pages long, and it's up to the user to choose the length of the desired summary. So let's start with the demo. This is the system, and we can access the first smart search service. As you can see, the smart search service is like a classical search engine. We can enter a query, but in this case, we can choose a collection of documents on which to issue the query. We have different collection of documents, and in particular, we have a collection for each thematic community of the InterRegMed program. So we have 8 different thematic communities. We have the blue growth, green growth, and social and creative community, efficient buildings, renewable energy, and urban transports, sustainable tourism, and biodiversity protection. So let's start with a query. For example, we use the query oil, and we select a specific collection. In this case, I'm selecting the collection Innovation Axis 1, which groups the documents belonging to projects in the thematic community of blue growth, green growth, and social and creative. If we issue the query, the system will return a list of documents. It works like a classical search engine. So we have a list of documents, and we have this relevance bar, which highlights the relevance of this document with respect to the query. Of course, the longer the blue bar, the more relevant is the document with respect to the query. Before examining the list of results, it is worth to notice that the system returns a set of related concepts. In this case, the system returned concepts very similar to this query, which are extra virgin, olive millers, olive oil, olives, polyphenols, and so on. So it seems that this query, these words, is used in this collection in the sense of olive oil. And we know that oil is a polysemous word. It has more than one meaning, at least in English. These are the related concepts. It means that if we analyze the geometric space which are built by the distributional hypothesis, oil and these concepts will be very similar and will be very close in that space. Now, let's try to issue the same query, but to change the collection of documents. For example, we use this collection, Low Carbon Economy Axis 2, which contains all the documents of projects in the thematic communities of related to efficient buildings, renewable energy, and urban transport. If we issue the same query, so the same query oil, but on a different collection, of course, the list of results will be different, but if we take a look at the set of related concepts, we could observe that now the related concepts are related to fuel oil, oil diesel, diesel gasoline, diesel propane, kerosene. So it seems that in this collection of documents, oil is used in the sense of combustible and not in the sense of olive oil. And this distinction between the two different meanings of the same words is obtained in a completely unsupervised way. There is no intervention by human, but it is the distributional hypothesis that now, in this case, if we analyze the geometric space built by the distributional hypothesis, we could observe that oil is very close to these other concepts. Now, if we take a look at this list of results, we can see that there is, for each result, the name of the document returned by the semantic search engine, a brief summary, and we have the name of the project to which the document belongs to and the overall budget allocated for the project. We could ask the system to show some metadata associated to each document. In this case, we have the date of production of this document, some keywords, target audience, and also the budget allocated to the deliverables. These are specific metadata specific for this usage scenarios, but of course, we could integrate and we could represent any metadata we could deem as useful. We could also take a look at the partner details. So in order to this project, we could list the partners and we, for each partner, we have the name, the fact that it's a lead partner of the project or not, the overall budget allocated for that partner, and also the country. If we click on the document, we can obtain we link to the document to the web page of InterregMed website, and we could also take a look at the document. Original PDF or words or of the document. In this case, the document is 18 pages long, and it's about bioenergy, biomass, and so on. If we, come back at our system, and if we do not have time, for example, to read the Word document, we can ask to the system to automatically summarize the document. We can choose the length of the summary, for example, in terms of number of sentences or original percentage of the original length. For example, we asked the system to produce a summary of which is 3 sentences long, and on the fly, by relying on the semantic, on the geometrical model, on semantic space built previously, the system is able to provide a very short summary, which is related to biomass fuels. So it seems it's quite relevant. But of course, if you would like to have summaries which are longer, we could also proceed with asking more sentences. Finally, the system allows to arrange all the results in this screen also on a thematic map. So we ask the system to show on a map the distribution in Europe or around the world of partners working on these projects and the budget invested by these partners for producing all these deliverables. So we asked to the system to show the thematic map, and in this case, the system can show the map, and you can switch between a map containing only lead partners or all the partners. In this case, the map contains just lead partners. There is a specific marker for a partner, and each marker is related to a specific community. If we click on a specific marker, we have the name of that partner, the fact that it's a lead partner, the name of the community, the name of the project, and the overall budget invested on deliverables by those partners. And in this case, we have also the two deliverables on which the partners has contributed, the partner has contributed. So this is the first set of services built by leveraging the semantic framework. In order to end my presentation now, I will give you some details about the second service implemented by using the semantic framework. The service is called policy design variable. The policy design variable is a more advanced service, which is more for maybe for policymakers. And the service allows you to create a cross-correlation matrix using some concepts which could be autonomously defined by user, of course, by leveraging the knowledge contained in a specific collection of documents. The main objective of this use case of this service is to help policymakers or some expert user to complement their top-down vision with a bottom-up approach, which leverages all the project outcomes contained in deliverables, technical reports, policy text, to possibly unveil meaningful connection useful to the policy-making process. As for the smart search, I will show you the potential of this service by using a demo. Okay. So this is the list of analysis. So when you click on the service shows a list of analysis which have already previously defined by other user. And for each analysis, you have the name of the analysis, the collection on which the analysis was performed, the author of the analysis, the creation date, and a brief description. We could create a new analysis, that is, we create a new cross-correlation matrices, and we can ask the system to create a cross-correlation matrix, and we could define the number of rows and the number of columns we need. For example, we need a matrix 2 by 3. We select a collection of documents on which to perform the analysis, and we ask the system to generate the structure of the matrix. In this case, we have an empty structure of the matrix, and in order to go on to proceed with our analysis, we have to define each concept on each column and each cell, each row. So each concept could be autonomously defined by user. For example, I can define a specific concept, for example, marine renewable energy. I use a label, and I use a textual description for defining my concept. In this case, for example, the text could be as long as you want. Maybe you could also upload hundreds of pages of text related to the definition of this concept. In this case, I use a very short sentence for defining the marine renewable energy. And this is the energy which can be harnessed from the ocean or the marine wind. It's comprised of 5 main types according to the origin of the extracted power, namely marine wind, surface waves, tides and currents, and thermal and salinity gradients. When we ask the system to generate a semantic representation of this concept, the system performs on that text, a natural language processing pipeline similar to the one used to process documents, and the system tries to identify in the text all the concepts which we are able to find in our semantic model. So the system has tokenized the text, has removed words which are not useful, for example, some conjunction or some we call stop words, words which are not interesting for our semantic analysis. We can decide to unselect some tokens which are not useful for defining marine renewable energy. And the system also, in order to enrich this representation, also provides some other concepts which seems to be correlated to this one. So we can select and enrich this representation with other concepts such as I don't know, mild winters, Atlantic Ocean, wind farm, or hot summers, or renewable, and so on. When we save and close this window, the system has defined the first concept, and there is a tooltip which provides you, which reminds you the list of concepts you have used. Of course, you can also select and unselect concepts according to your definition. Once we have finished with the definition of all the concepts on the columns and on the rows, we can ask the system to fill in the matrix. In order to show you how to fill in the matrix, I just show you an already previously defined analysis. This is a cross-correlation matrix which crosses together. On the columns, we have the three main pillars of the Thalia vision, and on the rows, we have the 6 features identifying the MED projects. When we ask to fill in this matrix, the system fills in each cell by retrieving the concepts which are mostly correlated to the concepts on the column and the concept on the row. So in this case, we have a set of the top 10 concepts which are correlated to community scale partnership in this case and cultural anchoring at the same time. By looking at the concept in each cell, it is possible to formulate 2 interpretations. We have a descriptive interpretation based on the assumption that those concepts mirror some evidence coming from the deliverables of the running projects, and one prescriptive, which highlights the gaps in the previous analysis and the possible action items for the policymaker willing to reinforce some of the correlation documented in each cell. So this ends my presentation, and this is what I have presented is a concrete way to provide support to the policymakers, starting by this services leveraging the Semantic Framework platform. So thank you for your attention, and happy to answer to your questions.
Thank you.